All right, this is Honors Algebra 2 Pre-Calculus. We're doing 4.1 in Pre-Calc. This is our second video in the series. So complementary angles sum to a right angle, meaning 90 degrees or pi over 2 radians. I always remember this stupidly as people compliment you when you're right, which is a pun because it's a different complement than the one that's mentioned for angles, but compliment you if you're right helps me remember that complementary are right angles. Supplementary angles sum to 180 degrees or pi radians. So one way that I remember this is that you take supplements to make your diet full, and supplementary makes a full line. Whether that helps you or not, up to you. So when we talk about complementary and supplementary angles, we're talking about positive angles. So if an angle is greater than 90 degrees or pi over 2 radians, it has no complement. Similarly, if an angle is greater than 180 degrees or pi radians, it has no supplement. So let's go ahead and walk through this. All right, so find the complement and supplement of the angle. If there isn't one, write none. Okay, so pi over 12, right? So let's start with complement, right? So the complement would essentially be a right angle minus the pi over 12, right? So that's going to be, if you get a common denominator of the easiest one is 12, right? So I'm going to get 6 pi over 12 minus 5 pi over 12. Sorry, minus pi over 12. My brain jumped to the 5. Ignore me. Minus pi over 12, which gives me 5 pi over 12. So the, or 5/12 pi, either way, right? So that's my complement. The supplement, right? So the supplement would be pi minus that value, right? Pi minus the pi over 12. Well, that's a 12 pi over 12 minus a pi over 12. So that's an 11 pi over 12. All right. If we do this with degrees, which I think is the one you're going to find more intuitive, right? So my, sorry, I don't mean theta. My complement would be 90 degrees minus the 85 degrees, which is 5 degrees. And again, I think most of us are much more likely to think, oh yeah, this is great, I can think in degrees. My supplement is going to be 180 minus the 85 degrees, right, which will be 95 degrees. All right, go ahead and give that a try. So go ahead and find a complement and a supplement for each. So I'm just going to say comp and supplement because I'm lazy, right? So comp and sup. All right. So for pi over 5, right, that's going to be a pi over 2 minus a pi over 5, right, which is the only common denominator they're going to have is 10, right? So that's going to be 5 pi over 10 because I times by 5 over 5 minus 2 pi over 10 because I multiply by 2 over 2. So I'm going to get 3 pi over 10. For the supplementary angle, it'll be pi minus that pi over 5. Well, that's a 5 pi over 5 minus a pi over 5, which is a 4 pi over 5. Complementary, so there won't be one for the complementary angle because 130 degrees is bigger than the 90 degrees. Now, if you hadn't seen that, if you had tried, you would have gotten that this was 90 degrees minus 130 degrees. You would have gotten a negative 40, and you would have realized, oh, hey, that means none, right? So if you had done it, if you didn't see it, that's fine. Supplementary would be 180 degrees minus the 30 degrees, which is a 50 degrees. And again, most of us are probably a little bit better at the degree stuff. All right, so one formula that I didn't specifically give you when I was explaining what a radian is, but one way to establish what a radian is to measure this arc length, right? So to measure this length along the edge of a curve, and you can call that S, right? So this would be S. And if you put the ratio of S over the radius, you'll get the number of radians. And that makes sense because if you picture what's happening here we have a single radius length as S. So my number of radians is R over R, which is just 1. And you can see that this is 1 radian, right? That was the example used for 1 radian. Similarly, right, if I went all the way over to here, right, if this were a 180, right, we know that that's half the circumference, meaning that we would have so the circumference would be 2 pi r. That means that this top measurement must be half of that, which is pi r. And sure enough, you get pi radians. So we can use the arc length measurement around the edge of the circle to establish how many radians are being used. Now, we don't really use it that way very much, but we can also manipulate this formula, theta equals the arc length over the radius, by solving for the arc length, right? So I can write, instead I can multiply this r over, and I can write that the arc length s is equal to r times theta, where theta is measured in radians. So there's a couple reasons that that's useful, right? So if you're trying to figure out, let's say this is a wheel on a bike. If you're trying to figure out how fast the bike is traveling along the ground, you don't actually care about the rotation speed of the wheel. What you care is how fast a point on the wheel, like this point right here, how fast does this make the loop? That's called linear speed. How fast does something on the edge of a circle travel in a line? Because if you're picturing it, what happens when this bike rolls is it rolls, so this spot is going to roll around the circle, right? And as it rolls around the circle is going to go like this until eventually we get back to that same spot being on the ground, right? That same, so if you put a little like chalk mark on a tire and it rolls, the tire's going to roll, 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 and at some point that chalk mark's going to be at the bottom again, right? And that's going to keep happening. So this distance along the ground is 2 pi r. Like that's one circumference. It's how long it took the circle to roll along the ground, okay? So if you want the linear speed, you want how long it takes to make that distance, that arc length, in a certain amount of time, right? That would be the linear speed of something on the edge of the circle traveling. However, the angular speed, right, which is how fast the inside is spinning, that's a measurement of theta, that central angle that we've been finding, that angle at the middle of a circle, theta, divided by the time. That would be more relevant if you were, let's say, the person spinning on an amusement park ride and you wanted to figure out how fast you were spinning and how likely it was that you were going to boot, right? You could figure that out by how that angle is changing. So that's angular speed. So we're just going to walk through a couple of quick examples, and then we'll move on. This is definitely something that you'll see more in like a physics class, but I just want to throw it out there so that you're familiar with the concept. Okay, so a lawn roller with a 10-inch radius, in this figure, you see it, makes 1.2 revolutions per second. Find the angular speed of the roller in radians per second, and find the speed of a tractor pulling the roller, meaning what is the linear speed, right? So that's a clever way. This is saying, hey, there's something pulling this thing. What's the linear speed, right? So this basically part A is asking you for the angular speed, and part B is asking you for the linear speed. So we can figure out, so basically there's a couple ways to think about it, right? But if you want to know, so this thing is making 1.2 revolutions per second, right? So in part A, right, we know that 1 revolution is 2 pi radians, right? So 1.2 revolutions, right, you could convert by saying that's 2 pi radians over 1 revolution, right? So you can figure out your angle theta by saying, hey, it's whatever 1.2 revolutions is. Well, that's 2.4 pi radians, right? So that's my angle. That means that my angular speed, right, my angular speed is going to be that angle theta, 2.4 pi, over how fast it happened. Well, they said per second, so in 1 second. Now, I could leave my answer like that, or you could type in what 2.4 pi is if you wanted. Technically, 2.4 pi is a more accurate answer, but if you're actually talking about measurements, a lot of times people want a decimal value. So it's either going to be 7.539 or 7.540 radians per second, or you could write it as 2.4 pi radians per second. Either of those answers would be fine, right? And then for B, right, so 1 revolution, we know that 1 revolution is the same as 2 pi times the radius in inches, right? So 1 revolution is 20 pi inches, right? And so the question is, how far does this thing travel in 1 second? Well, it makes 1.2 revolutions, right, which we know is equivalent, 1 revolution is equivalent to 20 pi inches. So 20 pi inches over 1 revolution, I can cancel that revolution, right? And so what's going to happen, I'm pretty sure that'd be a 12 times a 2. So I think we get 24 pi inches, right? Which, again, I could approximate, right? Now, that's fine, right? That's the distance that's covered. But that's going to mean that the linear speed, right, how fast this tractor is pulling, is the 24 pi inches per 1 second. And that answer's great, and you could totally keep it. You could also divide. Now, notice this happens to be 10 times bigger, basically. Like, that's the entire difference. It's just 10 times bigger than the other one, so you could probably figure that out. But I'm just going to hit second enter anyway and put 24. And sure enough, it's exactly 10 times bigger, but it makes sense if you look at the two answers that was 10 times larger. And that would be inches per second. Cool. So we have our angular speed and our linear speed. And again, the tractor is pulling it as a linear speed because the tractor is hooked up to this and pulling this way, right? The tractor is driving. I don't know. I can't draw a tractor. That's a tractor, people. It's not a tractor. It makes me sad. All right, cool. Okay, the second hand of a clock is 10.2 centimeters long, as you can see in this figure. Find the linear speed of the tip of the second hand as it passes around the face of the clock. So only want linear speed here, right? Okay, so we know that if we're trying to find the distance that's traveled, right, there's a couple different ways to do this. I'm going to argue that the easiest option is just to do the distance in a full minute, right? So they don't tell you units. They don't say do they mean seconds or minutes for units. They don't tell you. So since they don't tell you, I guess I'll probably go seconds because it's the second hand, but either of them would be fine because they didn't actually specifically ask you. So we want to do the distance that it travels over the time, right? So my argument is going to be that this thing travels a full circle in a minute, right? So in 60 seconds, we have one revolution, right? But we know, right, that one revolution, because we want the linear speed, right, one revolution is 2 pi times the radius, which is 2 pi times 10.2 centimeters. So basically, the distance this thing is traveling is 20.4 pi centimeters in 60 seconds. And I could leave my answer like that, right, or I could type it in a calculator. If you were asked to use different minutes, right, you could have made this 20.4 pi centimeters over 1 minute if you'd used minutes instead, right? And either of those is fine, right? You could find an approximate answer. You just have to make sure that your units are correct. So 20.4 pi, right, is this. So this would be centimeters per minute, right? But guessing that they probably want it in seconds because they're talking about the seconds hand, it would be 1.068 centimeters per second. Right, so that's how fast this thing is traveling. And again, either of those would be, either of those are an okay option. They didn't specifically say, they just said linear speed. They didn't say in, centimeters per second or centimeters per minute or even centimeters per hour, although that would be a lot of centimeters anyway. All right, we're going to talk real quickly about one more way to measure angles. This does not come up a lot, but I just want to throw it in here in case you see it in a problem in the book or anywhere else. Honestly, if I see this notation, I instantly change it to degrees because it's just not worth it. So another way to measure degrees is called degrees, minutes, seconds. And it's got the degree symbol, and then the minute symbol is an apostrophe, and the second symbol is a quotation mark. Angles can be measured in degrees, minutes, seconds. This is just a more precise way to write angles in degrees, right? So you can see this in maps and GPS a lot. So actually, here's our school, right? So this is one way to write the latitude and longitude of our school. This is another way using degrees, minutes, seconds. And you can see, so here's degrees, here's minutes, here's seconds. And you'll see that a lot on like GPS stuff, right? Basically, the conversion factor is the same as hours, minutes, seconds, right? So I can actually show you how we could convert this to this, right? So let's just walk through it real quick, right? So if I wanted to do this by hand, right, the way I would convert this is I would write that this is 39, because that's the degrees, right, plus the minutes over 60, which would be 58 over 60, right, plus the seconds, which in this case is kind of ugly. It's 58.0764 over 3600, and that would be the number of degrees. And I'm going to go ahead and type that in, and you're going to see that that actually comes out to be this latitude. So, so if we did 39 plus, it's a 58 over a 60. Oh, that's not over, my bad. Divided by 60, right? Plus 58.0764 divided by the 3600, right? And there you go, right? Same answer. So, so just to show you, that's definitely an option, and we'll, yeah. So I was going to take a screenshot, but there's no reason because it's a video. You can pause. So I usually do this. There is another way to convert things from degrees, minutes, seconds, right? So the other way to do it in your calculator, you'll notice that there's an angle button right here. And so there is, under angle, there is a DMS option, right? So you can convert things to DMS, right? If you wanted to convert this to a regular angle, one way you could do it is you could type in 39. If you go over to angle, right? Sorry, I meant second angle. My bad. If you go to angle, you'll see right away there's the degrees and the minute symbol. So there's degrees, right? 39 degrees. And then I go ahead and type in the 58, and I go back to angle, so second apps 2. And then the tricky part here is that you can't type in You can't type minute, minute. That's not how it works. So it's tempting to think, oh, hey, there is no second symbol. What do I do? But there actually is a second symbol because there are quotations on your calculator. I'm looking because I'm kind of blind as a bat, but there are quotations on your calculator. There they are. They're right over the plus sign. So if I hit alpha plus sign, there's the quotations, right? So that's where it is. And then I hit enter and look, it does it for me. Similarly, you could go to angle. So if you go to angle, so second apps, and you go to angle, you'll see there's a DMS arrow. You can convert something to degrees, minutes, seconds using your calculator. Now you'll notice it might be slightly less accurate because they gave me one more point here than they gave me here, but you can convert things using degrees, minutes, seconds. So we're just going to walk through real quick, converting real quick, and that's it, and that'll be the end of this video. All right. So give the DMS notation, given the DMS, convert it to degrees. Again, one option is to just type it in your calculator. So you could hit second enter, and you can say, cool, I'm just going to overtype this. I'm going to make this a 38 degrees and a 15 minutes and a 900 seconds. And that's fine, right? That's fine, and you can hit enter and it'll do it for you, okay? I end up getting that this is a 38.5 degrees, right? And that's fine. The other way to do it is to do 38 plus the 15 would be over 60 because that's minutes, and the 900 would be over a 3600, right? And then hit enter, and if you type that in your calculator, you're going to get 38.5, right? It doesn't matter to me which one you pick. Now I'm going to do the second one that way because I think it's pretty straightforward to type in the other one if you want. So this would be a 301 plus a 55 over 60 plus a 200 over the 3600. Right, and then I'm going to get an approximate answer. I didn't have to write approximate for the top one because I wasn't rounding that. It really is a 38.5. So 301 plus 55 plus, 55 over 60, plus 200 over 3600. And there you have it. So this one is rounded, so 301.972, right? It's approximate. All right, so real quick, after we do the last one, I'll just walk you through why this is useful, because it does matter. Degrees, minutes, seconds is useful in things like navigation. You're probably not going to use it unless you go into a field that uses navigation, but I'm just saying. All right, so if you go ahead and put this in your calculator, right, you could even just hit second enter if you've already done one recently, right, which I did, so I'm going to be lazy. So this is a 210 plus a 5 over 60 plus a 3000, so 300 second insert 0. All right, and I get that this is approximately a 210.916 or 7 degrees, right? I think I put a degree symbol on the other ones. I didn't. Don't forget your units. All right. And then for this last one, I'm going to hit second enter. And again, you can just do degrees, minutes, seconds if you want. There's, you can certainly find the degree symbol. I think it takes me more time to do that than it does to just type this in. Second insert 3, and this is a 1500. Right. That turned out surprisingly nice. Yeah? Okay, cool. So surprisingly, that's literally just 73 degrees, which I am surprised by. Did I do something silly? It's possible. Oh, I guess because I could have simplified the last one. Oh, well. So I picked this I shouldn't have picked because it could have been simplified, but that's okay. We'll survive. Anyway, so why is this useful? So if you picture a plane flying across the country, right? So if you picture a plane like leaving Philly and flying across the country, when they set on a heading, right, if you're flying, even a really small angle difference when you leave Philly could have drastic consequences flying on the same path when you get across the country, right? So as silly as it seems, like when you're talking about headings about like launching things into space or drones or planes or boats, small differences in degrees are very, very important. So that's one of the places you'll see degrees, minutes, seconds is in all sorts of navigation. If you go into any sort of aerospace or pretty much anything nautical or anything with, aerospace would include planes, anything that involves travel or GPS or mapping, you'll find that degrees, minutes, seconds is pretty common. All right, that's it for this video.